nanohub.org.
Online simulation and more for nanotechnology.
Okay, now this is great. This is a fun illustration. I don't know if you ever saw this before, but basically what this is showing is like how you can lay underwater fiber optic cable. It's like a little animation. And so since I'll be talking about optical telecommunication links, then basically you can see kind of like, obviously a somewhat oversimplified process, but it's kind of showing how you kind of like put down the initial cable, connect it to land, and then how you set up a boat and the anchor, and then basically the boat and the anchor will kind of go along together to make sure that the cable is being buried. And then I guess when you feel like you've gone far enough, then you can connect it with the next one, and then you have like a whole system. So it's pretty fun animation. You all see that? Okay. So remember in the first week, we talked about how these optical telecommunication systems work. And we said they're basically like, three kind of key elements: the transmitter, communication channel, and the optical receiver. And that's how you take your input data and then output it somewhere else, right? So now I wanted to kind of focus a little bit more on what the communication channel looks like. Okay, so there are different topologies that you can have in these sort of systems. And the first topology is very straightforward. It's essentially a point-to-point link. So you can think of it kind of like a direct flight for your light. And the only catch is that sometimes you need to have an amplifier. So you can't necessarily just have a single fiber without any amplification that goes from, say, West Lafayette to China without any help. So there is a need for amplification. And the old school way of doing this is basically you would have a regenerator. And so the concept of the regenerator is you send it a certain distance, and then you capture the light as a signal, and then you basically translate it into electrical signal, and then you immediately output it on the other side as another signal, and then you put it into next link of fiber. Okay, so obviously that could work, but you realize that it gets really slow if you have a lot of losses in the system, or if you're going really long distance, especially if you're going like trans-Pacific, it becomes like kind of untenable in many ways. And so I think since the early 90s, at least, there's been a big shift to optical amplifiers. And so optical amplifiers, we'll talk about more next time, but they're actually closely related to lasers in the sense that they use stimulated emission to amplify your input light directly in light. And so it's purely analog light-based amplification. So there's no intermediate conversion to electricity. And even though we're electrical engineers, we also recognize good engineering when we see it. So in this case, avoiding the electrical pass-through or component in between is important. So that's like kind of the go-to strategy nowadays for point-to-point. And there are not just point-to-point, but there are many other types of topologies out there. And so another type is actually two types of distribution networks. And so here, really the concept would be if you have to communicate with, like, say, a bunch of people in a neighborhood. So like home internet service is a good example. So many of you have probably experienced this, like in your own home. And so there are actually two different topologies that are most popular. The first, the hub topology shown on the left, basically it's kind of a hierarchical pattern where you have like kind of a central hub, and then you split it off into two or more different hubs, and then each of those hubs has either sub-hubs or it has individual nodes. And you just keep like splitting the signal progressively. And so if you're trying to take a single amount of information and then farm it out to a lot of different users, then this is a good topology. But if you need to go the other way, obviously it creates a lot of overhead. So it's not necessarily great in every case. Another approach actually is shown on the right, which is like kind of the so-called bus topology. So the idea there is you have a single bus, and the bus basically is like your main carrier of information, and people can take their data and kind of hop on or off the the bus, if you will, using basically individual nodes that are connected to the network. So that's basically a concept. So in principle, it's very simple. And for a small number of users, it works well. But as you can imagine, if you have like, millions of users on a single bus, it becomes like a tremendous amount of overhead. So this latter bus topology is not really scalable to tremendous number of users, whereas hub is better if you have large number of users, as long as they don't need to go the other way. Now, of course, there are other topologies out there. In fact, if you go to Purdue, then we probably have like one or two of these different types of topologies. And so this is like, if you want to have many nodes communicate with one another in kind of equal footing, right? So it's kind of arguably a democratic way to look at things. Then there are basically two types of topologies. And then the first topology on the left is called a ring topology. And so as you can see from just the illustration, the idea is basically like all the users are kind of on this ring. And they can basically just put information onto the ring, and then they can go back to the other nodes. And so the difference between this and the bus is not tremendously huge, but obviously you can see that in the bus topology, there has to be essentially like kind of a beginning and end to that information flow. And then of course, ring topology, the idea is like, you have like everybody's on equal footing, so there's no real beginning or end. And again, this has one of the same weaknesses as the bus topology, which is it can't accommodate like huge number of users. So then if you have a big network like Purdue's, then you might actually go to more of a star topology. And so the idea is basically that there are a bunch of individual subnetworks, and all these subnetworks kind of connect to a central router or kind of like the core of the system. And then of course in individual networks, you could still have like a ring topology, but that kind of makes it more manageable. And so in many cases, you could also have like a ring star hybrid. So it's like basically the star is like the high level architecture. And then in each individual networks, you may have like a handful of rings for, small number of nodes. But that's how you can kind of structure a lot of these communications, so-called local area networks. So any questions about that? I mean, maybe you already knew a lot of that. But okay. Well, I can't take credit for this one. This was from Wikipedia. But it's fun showing, laying out the cable. Okay, so if no questions then, so let me talk a little bit about what are the limitations on these systems. Okay, so one big limitation, of course, is kind of the issue of loss, which we just alluded to a few minutes ago. But then there's another issue which is almost equally important, which is dispersion. And remember we said basically like the time difference of arrival of signals at say different wavelengths is going to basically limit the bit rate at which we can communicate. And so what this is showing basically is that if you don't do anything about dispersion, okay, then as you go to longer distances, then the bit rate starts dropping tremendously, right? So if you start talking about going across the Pacific or something, you're going to be limited to below 1 gigabit per second, which maybe it's okay for like individual user, but if you're talking about entire countries communicating with each other, that's really pitiful amount of bandwidth. So then the way to address this to some extent is take this dispersion value, which for just kind of a single mode fiber without any special features would be maybe on the order of 17 picoseconds per kilometer nanometer. And then you can use different types of fibers. Obviously, it depends a lot on the application, how high end you want to go. But the best case, this red curve, is the dispersion shifted fiber. And then you can see that this kind of a log scale, so you're going from less than 1 gigabit per second to something on the order of maybe like 25. So you have like a pretty big improvement, like maybe on the order of 30. And there's a whole paper that kind of talks about like, how much prospect is there for further improvement in dispersion and loss that I cited here, in case you're interested. It's like the roadmap for all optical communications in the future. And then going back to the loss constraints. So of course, the key thing here is just that you're limited by kind of the amount of receiving power that you can tolerate and still get a signal. And then of course, the maximum transmission power. So, and this equation is basically giving you like, what is the maximum range L before you have to have some amplification. So this is actually telling you that in many cases, increasing power factor 2 does not increase your range tremendously. It's like on the order of log base 10(2), which is maybe like 0.04 or something 0.4 or less. So it's pretty small. And then the other thing, of course, is that there are different channel losses as well as system kind of variability. So oftentimes it's like a system margin, if you will. So basically what this is showing you is essentially you can compare using a laser for like a 0.85 micron light wave system. This was obviously much earlier than kind of the current systems, but this just giving you an illustration of what used to be used. So you can see that for the laser system, oftentimes you have higher power. And here the power is written in units of dBm. Are any of you familiar with that? Okay, so you already seen that? Okay, good. Okay, so the receivers are the same, of course, for both cases, laser and LED. But the laser may have to tolerate higher channel loss, and so that it comes up as CL here. And of course, you have fiber cable loss and connector loss that are basically the same at a given wavelength, right? But then you can see that even though the laser light is like maybe order of magnitude larger, in practice, the max length that you can tolerate before amplification is not that much greater for the laser than LED for this system. And of course, there are other systems now that have much lower losses, so that's why we can go well over like 10 kilometers nowadays. But this is just kind of a case study, if you will, of this kind of problem. And then for the dispersion, going back to that, so basically what this is basically trying to get at is this kind of fundamental limit, which we talked about in the first week, which was just that the bit rate times the time delay has to be less than 1. Otherwise, basically, your first signal starts overlapping with the second signal, with the third signal, and then you can't tell what information is what anymore. So this basically is just taking that b delta t less than 1, and then looking at so delta t as a function of dispersion, which is beta times beta 2 times our L, which is basically the length. And then remember, we showed earlier a couple of slides ago, there's this dispersion. So you can see that basically to get like the overall time delay, you have to take that dispersion parameter d, multiply by the length of the fiber L. So you have d times L times this delta lambda, which is the spread of wavelengths. And that gives you an approximate expression for the time delay. So then if you said, let me write this down, b delta t less than 1, and then you set delta t is equal to dispersion times length times the wavelength spacing delta lambda. Okay. And then you plug in the values. Then you basically get that b is less than 1 over delta t, which is 1 over dl delta lambda. Right, so that's basically putting upper bound on your bit rate. If you multiply by L on both sides, then obviously this cancels. So you get 1 over d delta lambda. And here we just assume that delta lambda is 4 times the standard deviation of the range of wavelengths associated with your source, right? So this actually tells you now that if you have like a narrow line width source, or basically a small delta lambda, then you have like a higher upper bound for your bit rate. right? So that's really the key takeaway. And you can also potentially couple to single mode that will allow you to reach like what we call the ultimate dispersion limit, which is basically a limit where you're not being constrained by the source, but you're just being constrained by the fiber. And so then here, basically, the delta lambda is exclusively coming from the fiber. And so this is written usually as the bit rate squared is times L is less than 1/16 times beta 2, where beta 2 is dispersion just of the fiber. Okay, so hopefully that kind of makes sense. But what this is basically telling us is that the nature of the source is a key determination of the ability to communicate quickly. What's that? The large B, that's our bit rate. So basically we want B to be high. So if we go back to this graph here, then it's basically this axis, the x-axis here. Sorry, I should have been more clear about the notation. And then there's another factor that's very important, which is essentially how quickly your signal can rise or fall, right? And so all of you know about RC circuits, so I don't have to explain that. But the point about this system is that there are basically several sources of basically effective capacitance in the system. One which is basically associated with the transmitter, right? So that's basically what we call T sub TR. So that's like basically a time constant that's built into the transmitter. And then the second term here, T fiber, is basically the rise time associated with the fiber. So once you send light into the system, how long does it take to reach kind of a steady state? And so of course the quality factor in principle should not be that high, but it can take a non-zero amount of time. So you do have to include that. And then of course the receiver itself may also have finite response time, which is known to vary a lot depending on what detector you use. Anywhere from ultra fast, like, on the order of picoseconds or less, to potentially like, having like, on the order of 1 second response time. And so that tells you right away that in addition to having ultra fast sources, or at least fast sources, you also need to have fast receivers on your system, because if you're basically using a really great like optimal laser system source, but your receiver is like, say, pyroelectric sensor or like a bolometer, like a thermal sensor, they'll never respond fast enough to give you any useful data at the receiving end. So that actually tells you immediately, like both the source and the receiver have to be accounted for in the design, and they also have to be probably comparable in terms of response time. Maybe even like the receiver being a little faster is ideal than the laser, which is already hopefully very fast. But I think, this very simple way to look at it, but basically all these response times add in quadrature when you add them all together empirically. So this is a very simple rule of thumb to say, like, how fast is your total system going to respond? And so again, we need this B delta T less than 1 to be true. So that means we also need the bit rate to be much less, hopefully, than this like T sub F, which we calculated from here, right? If the bit rate, or sorry, I mean 1 over TX. I wrote it wrong. Sorry. So if the bit rate is equal to or greater than that, then that means basically by the time we turn on a bit, then we're already trying to send the next bit, right? So then that becomes a problem, because we don't have enough time to send discrete pieces of information. It's all kind of getting blurred together. So that's another challenge in these designs. And so the last slide for today I wanted to show you is that a lot of these challenges can be overcome. So you don't have to just give up because these things are happening. In fact, if you look at this experiment, this was from a few years ago, but this was basically trying to look at what happens for a transatlantic cable, like how much capacitance can you get. And I think they even looked at, they looked at transatlantic, which was on the order of 7,000 kilometers. They also looked at a few trans-Pacific, which were close to 10,000 kilometers, right? So that's the Pacific, that's the Atlantic region, I think. And then what they showed basically is that obviously if you have like, a fair amount of dispersion, then you're going to be somewhat limited in capacity, but you can still actually overcome a lot of the issues that we were talking about earlier with the combination of fast source, fast detector, obviously the right choice of fiber, and most importantly, good amplification and good limitation of loss, so that the system keeps keeps the signal coming without any substantial distortion or aliasing between different bits in the system. And so obviously there are many other tricks that they played in this experiment. So I haven't talked about all of them really explicitly, but part of it is like they're doing multiple wavelengths and multiple channels, and they're using like fancy encoding algorithms, which we'll talk about later. So they're doing a lot of things, but basically they're able to get, in the best case, experimentally up to about 50 terabytes per second, which is much, much better than what we predicted in this earlier thing, where we were basically saying 10,000 kilometers would be like maybe 1 gigabit per second. So we're basically like many orders of magnitude above that, like on the order of like, I guess it's about 50,000 times higher than what was predicted for like a poor quality fiber and source and receiver. So there is like a lot of potential to overcome these issues, but also just wanted to emphasize that it's non-trivial. Okay, so any questions now? All clear? What is PB? Oh yeah, so this is basically how they're measuring dispersion. So it's like petabytes per second per kilometer. So this is basically these are essentially analytical curves predicting like what capacity would be associated with each of these dispersion values. And then here's like, the dots are basically what they saw experimentally. If they just use one band, so that's basically blue. And then if you look at the red diamonds, then that's basically using both the C band and the O band. So it's two separate wavelength ranges. And of course, they had multiple channels within each of those ranges. So a lot of the trick was just do many, many bands and have them not crosstalk to each other. But there are also many other tricks involved, right? So I don't want to say that we've explained all the tricks yet, but just to emphasize that you can overcome a lot of these issues with proper design and engineering.